Hello, greetings from Nottingham. I am Abhishek. I am a master's student at Nottingham Trent University, and today I will be presenting our team's work on tactile sensor array-laden 3D printed soft robotic gripper. This is the content of my presentation. I will start with the introduction. Recently, soft robotics, a field of robotics that aims to construct robots from highly compliant soft materials, has gained much attention. Soft grippers are one of the output from soft robotics research. Conventional rigid grippers used in robots are prone to cause damage of delicate objects such as fruit while handling or may push it out of the desired path. Soft grippers are advantageous in this regard and with the sense of touch can be used to lift delicate objects without damaging them. The sense of touch will also allow them to enable a closed loop gripping and to avoid slippage. This table here summarizes the prior art on soft grippers with embedded sensing. There are few prior works with soft grippers employing embedded sensing, primarily employing pneumatic actuators. Pneumatic soft grippers are well suitable for high-speed actuation but require cumbersome compressors, airtight tubing, tethering, and chambers. For applications which do not require high-speed operation and where the overall process speed is primarily dictated by the speed of the motor-driven joints in a robot arm, tendon, or motor-driven soft end effectors offer a compact, easy to integrate solution. Further, we have combined tactile sensing with vision to carry out a pick and drop task. Next, I am presenting the block diagram. This block diagram shows the complete system implementation. This block diagram has three major information flow paths. Flow path 1, where the task scene was captured by a Microsoft Live HD video camera and the video feed is fed as input to a TensorFlow neural network, which is being used to detect the object. A capacitive sensor array has been fabricated, which is embedded within the soft gripper. A program developed in robot operating system was used to move the robot arm to the object location with the grippers in an open position. The robotic gripper is then made to grasp the object, and as soon as it comes in contact with the object, the capacitance of the custom capacitive sensor array starts to vary. The capacitive sense variation is converted into a digital signal and is being used in a closed loop to grasp the object without damaging it. Now to the design and fabrication. This figure shows the 3D design of the soft gripper. The soft gripper was designed in Autodesk Fusion. It has a housing for a linear actuator. The electrodes were designed separately with a pair of electrodes for each phalange to suit the 3D design. The electrodes were fabricated employing a 2D process. After fabrication of electrode, they were embedded during 3D printing of the soft gripper. The final gripper mounted on a robot arm is shown here. Electrode fabrication and sensory mechanism. The electrodes were designed to ensure minimum cross-coupling between the individual sensors while ensuring compliance, stretchability for robust integration with the tri-gripper. The flexible electrodes were fabricated using a 2D toner transfer process, resulting in flexible copper electrodes and interconnects in polyimide film. While 3D printing the gripper using TPU, the printing process was paused twice during the print to introduce ground and sensory electrodes. The 3D printed material itself is used as a sensory dielectric. When a pressure is applied, the TPU, which is acting as dielectric between both electrodes, undergoes compression. This results in change of distance in the parallel place capacitance equation, which is capacitance is equal to epsilon multiply area by D. The capacitance variation is measured to the end of both of these electrodes. I will present the results in the forthcoming slides. I will start with the results of the sensors embedded in the soft gripper. The pressure versus capacitance characteristics of one of the sensor is shown in this figure. A non-linear relationship was observed for an applied pressure range of 0 to 150 kilopascal. These characteristics are divided into three regions, which are initial onset region, steeper region, and saturation region. In initial onset region, pressure is mainly getting concentrated in the cavities above the sensor region, while in steeper region, the dielectric between the electrode is directly undergoing compression, and in the saturation region, the sensor goes into saturation. The characteristics shown here are only for one sensor. The maximum sensitivity achieved here is 2.87% per kilopascal. Next, I will present the TensorFlow training part. The TensorFlow training and testing was done in NVIDIA CUDA GTX 1080 graphics enabled PC. 480 image samples were used for training and 120 image samples were used for testing the TensorFlow neural network. The figure shows the classification loss versus epochs during training. At the end of the training, classification loss of less than 0.05, localization of less than 0.012, and objectness loss of less than 5e is to power minus 4 was observed. This shows that objects in the frame were classified properly. A grasped apple is also shown in the sub-figure. This is pick and drop. Snapshots from the live videos of the gripper in action is shown here, and this is from a pick and place task. This shows the videos of the gripper in action. Tactile sensing part and pick and place task. Videos of the gripper in action, tactile sensing part, pick and place task. Let me conclude. A sensor array laden soft gripper that can be used to lift and grasp delicate objects has been developed. A representative tactile sensor in the sensor array exhibited non-linear characteristics with maximum sensitivity of 2.87% per kilopascal. The tactile sensing was combined with artificial vision machine learning to identify soft fruits with a classification loss of less than 0.05. A pick and place experiment was demonstrated. Thank you.